rock physicist, a rock mechanicist, who builds machines to answer questions we have about material behavior, such as the effects of fluids on attenuation. He develops new analytical techniques that are to do with digital rock physics, and all of these characterizations helps us understand processes from induced seismicity to reservoir characterizations to natural earthquakes. It's really remarkable to have someone who builds these new tools. The great thing is Nicola doesn't need much of an introduction because many of you have interacted with him. He's designed gadgets for your labs, and all of these things doesn't even begin to capture his interests. He's also into spelunking and has written papers on stuff like, I don't know, microbes in caves and things like that. So it's really great to have Nicola here. He joined us in 2016. This is his talk upon the proceedings of his promotion, of his tenure. And he's going to talk to us today about some of the things, some of the experiments he designed, and some of the insights on Earth behavior that he's gleaned from them. And his title is Earthquakes Under the Lens of Rock Physics. Nicola.
Thank you very much, Professor. Thank you very much, Professor Becker, Torsten, for the introduction. Thank you, Luke, for the introduction. Where are you? You're here. Okay. So I will try to be quick here. We have a couple of hours, right? I will try to go through my slides pretty quickly and let a bit of time for questions. And yeah, today I'm going to talk about earthquakes and how rock physics can help us to understand earthquakes. You know, we still don't have a unified theory that can tell us if a fault will generate an earthquake or not. And that's a big problem. We go in the field, we see faults, and we don't know. The faults might eventually generate an earthquake, or they might not. And that's a big uncertainty that we have to deal with. And unfortunately, we typically pay a very high toll every year in terms of lives and damages. So we want to solve that problem eventually. And rock physics makes a small part of trying to understand that. So before going to chapter 2, 3, and 4, I need to acknowledge that the work done in my laboratory is not only about earthquakes. I have done work on digital rock physics, for example, as Professor Becker was discussing. I will talk about the work of mainly 3 students. However, in my laboratory, I had many other students passing through. I have PhDs, masters, and also undergrad research assistants. And I would like to start from these 2 guys here. I'm sure you remember them. So Eric and Ken, they came here in 2016. And in the beginning of 2016, my laboratory was in a piece of paper, in our dreams, right? Nightmares sometimes. And at the end of 2017, the laboratory was finished. Time we put in machines and we start making and running. We stopped breaking stuff, right? 2018 came, and in the meanwhile, these students need to do something, and we designed a series of experiments, simple experiments, benchtop experiments. And I had a question in my mind, which was, can we simplify digital rock physics, which is very cranky and somehow cumbersome. And together we kind of demonstrate that we can estimate properties of rocks from images, from 3D models, right? Getting rid of segmentation, which is one of the big problems in digital rock physics. Going on, we had Michael McCann, who was co-supervised with Professor Spikes, and Michael studied the attenuation of waves, or seismic waves, in liquids. He remarkably built his own machine here, and he studied the attenuation of this jelly material, which is a guar gum, is a mixture of water and guar gum, which is a proxy for silicate melts, because also create polymers like silicates. And it shows that the attenuation goes up as you increase the quantity of the guar gum, and it goes up following, in fact, a theory which is pretty interesting. On the same line, I had a visitor student that came in 2019, and Zichi here studied the attenuation in bubbly liquids. And he also put together a very simple piece of equipment to study the deformation of bubbles. And it looks like trivial. However, if you look very well, the bubble keep deforming after the pressure here has reached a steady state. So, and also in this case, we kind of developed the theory that describes the shrinkage of this bubble beyond the change of pressure. And this work is in line with what I've been studying these last years. For example, I'm trying to understand what is the attenuation in magmas. That's very important because when magma changes and bubbles, for example, grow inside magma, if we have a variation of attenuation and we can detect the variation of attenuation, then we can maybe say, okay, we are close to an eruption. And then finally, I had a couple of URAs. Mason here worked on seismic monitoring, and Carol worked on the caves, on spelunking, like Professor Becker said, right? And so Carol studied the interaction between life and those amazing crystals that grows in this cave in Colorado. And here we are left with the last three students that went through my laboratory. And Ethan, Carly, and Omar, they pretty much all work on earthquakes. And here we go in the second chapter of my presentation today. So the chapter 2, the main actor, if you want, is Ethan, who published a paper last year, which is entitled The Influence of Frictional Melt on the Seismic Cycle. And I would say that we used a new way to simulate earthquakes in the lab that reveals the influence of weakening and strengthening mechanisms on the slip and the emission of seismic waves. And I want to mention that Ethan is co-supervised by many professors here, Professor Becker, Professor Stockley, and also Professor Facena. Maybe sometimes too many professors. Now, I want to make everybody on the same page here. As an earth scientist, we study earthquakes, and one of the aspects that we look into earthquakes is to understand the friction in rocks. Friction is one of the parameters that control the slip of a rock against another, right? I mean, earthquakes happens because rocks, they slip one against the other under huge amount of energy, and that's why fundamentally they destroy cities and they kill people eventually. And the friction coefficient, which was defined probably 500 years ago roughly by a person from Italy called Leonardo da Vinci, is defined as the ratio between the resistance that the block takes to move and the normal stress, how much weight you put on that block over there. In terms of stress, you can say that the friction coefficient is the ratio between the shear stress and the normal stress. Now, when the force applied on the block overcomes the resistance, then the block starts accelerating. And the acceleration eventually will dissipate energy at the interface between the two blocks. And there is where you have processes that eventually will destroy the material, will eventually create processes like flash heating and weakening, which is not this. It's flash heating and weakening. This is how I pronounce it. Maybe you understand something different. It's heating with an H. Okay? And why do we have such processes? Well, because again, we have energy dissipated at the interface. The heat might raise so much that the rock might even melt. And whenever you create a melt, you are now making your fault much weaker, and this allows the earthquake to propagate and eventually to become destructive. Now, to go a bit in the description here of the process, if we think about this experiment where we are trying to make this block slipping, and we are making it slip at a certain velocity, which eventually might be even zero, we do have a certain friction amount, which is here, and then we change the velocity, and then we suddenly observe an increase of friction. This increase of friction is called direct effect, or A, and then if the material reacts as we have seen by becoming weaker, eventually after a certain d sub c distance, we will have a lower friction value, and the difference, right, between the peak of friction over there I have this one, I can use it. Oh, the peak of here and the value over there is called long-term effect, or B, okay? Now, what does control if a material will be weakening, velocity weakening or velocity strengthening eventually? There are several effects, all the process I just showed. Another reason why you do have stable versus unstable behavior, the fact that some faults generate earthquakes and some other do not generate earthquakes, is due to the fact that you do have a critical stiffness, which is called Kc, which is controlled by the normal stress, those B and A that we just see, and the distance at the DC, the D sub C, okay? And when this critical stiffness is less than is more, sorry, than the stiffness of the system itself, in the case of a laboratory is the stiffness of the machine that we are using, then the system becomes unstable. And people have demonstrated, for example, Lehman in 2016 has demonstrated that this is the truth, right? If you increase the stiffness of the system, eventually the fault becomes stable, in the sense that it does not generate these huge stick-slip events, these big stick-slip events. Now, we are introducing the system a spring, right? So you see we went from a model where we have only a block with a force, try to move the block on the surface. Now we are adding a spring there, which is the stiffness of the system. Now, the spring is going to store energy and eventually release the energy that it has stored during the earthquake. And that is the key of the new methodology that we are using, which looks like, Lapalissiano, right? But it's not, because I'm going to show you very quickly that experiments in the past have been run without or even trying to avoid that stiffness and the accumulation of energy inside the spring. And it's kind of countersense, but it is like that. I want to say that because we are geologists, we like the outside, all these studies about fault zones, how fault zone structures are, how faults are embedded inside mountain range are extremely important, because now you see the stiffness around the fault is going to control if a fault eventually is or is not stable, right? So all these studies, for example, Mitchell and Faulkner in 2009, and many others, right, where they compare simple, this is very annoying, I'm sorry. So faults which are very simple with faults that instead have a very complicated fault zone, right, are extremely important to understand if in the field eventually a fault, or might be very important because we don't know yet how to respond to that question, if a fault would be seismogenic or if a fault will not be seismogenic. Okay, so let's go back to the laboratory, right? I just told you that people have been trying to avoid, in certain cases, to have that stiffness and that accumulation of energy. And if that is not true for stick-slip, it's for sure true for rotary shear experiment. And here we do have, stick-slip methodology, which is one of the greatest methods to study friction in rocks, versus rotary shear experiments. These are two of the biggest exponents of this technology and methodology to study friction. Chris Marone and David Gosby, they came to visit my lab a few months ago, and they're looking at the apparatus I'm going to describe soon, which I like to think is going to join together the stick-slip methodology with the rotary shear methodology. So stick-slip methodology and rotary shear methodology are two methods, and the other phase is that one is slow slip and the other is fast slip, okay? So stick-slip, slow slip rates, right, in stick-slip, for example, we typically have friction coefficient which are in the order of 0.6, but we know that when we shear our rocks with a rotary shear apparatus, for example, and we go a much higher velocity, much longer displacement, that friction decreases and it can go and fall towards zero. Is it in nature like that? It is. We know that in nature, during earthquake, we must have very low friction coefficient because, for example, we don't observe thermal anomalies. If the friction coefficient was 0.6 or 0.7 during an earthquake, we will see much higher temperature rise after big earthquakes, okay? So in stick-slip methodology, right, we do have the occurrence of spontaneous slip. We load the system as some energy stores energy, and then release the energy during the event. But the counterpart is that we do have very small velocities and slips in the order of millimeter per second, and slips distances in the order of millimeters. Here are some results from Lehman 2016 that he tried to change the effective stiffness of the system, and as you can see, the fault goes from an unstable behavior where he has this stick-slip events, so the friction goes up, and then an earthquake happens and the friction decreases, and then again it gets reloaded, and so on and so forth. Up to when increasing the effective stiffness, the system becomes fundamentally stable, and you don't have those big events anymore. Now, with rotary, right, you do have the advantage of being able to shear your rocks at co-seismic velocities and for distances which are typical of earthquakes. However, the interesting thing is that rotary shear experiments have been always, 99% of the times, performed by imposing the velocity and imposing the distance of slip, which is not what happens in nature. In nature, you do have those fault zones, the mountain range around the fault, which stores the energy and eventually releases it during the earthquake. And the fact that the fact that other people have tried to change this paradigm, right? Let's try to change the paradigm of imposing the velocity, such as Reches or Chang or Spagnuolo, right? I don't mention Rieger because Rieger was our student at ETH that do the master thesis on the machine I'm going to show. That demonstrates this idea that people have been imposing velocity and displacement, and that, what does take it away? The spontaneous events, right? Events do not occur spontaneously. We lose all the nucleation part, and eventually we lose what we call the co-seismic feedback. The fact that the energy accumulated and the rate at which the energy is dissipated on the fault feeds back into the slip velocity, the magnitude of the earthquake, right, eventually. The slip distance, together they make the magnitude eventually, right? And the weakening and strengthening mechanisms. And that's what we want to study. We want to study that feedback. We want to see what happens when a process occurs on the surface. How is it going to change the slip distance and the slip velocity, right? Under which condition I do have those processes, under which condition I don't have those processes, right? So the hypothesis here is that the slip behavior and friction are a function of the weakening and strengthening mechanism activated at high slip rate. And so we are working on this, and we are still working on this. And luckily we will work for the next 3 years at least. Now this is a cartoon showing you very quickly the difference, right, between an experiment performed with a machine which is imposing the velocity and the distance, right, and a machine that instead allows for accumulation of energy inside a spring, which is placed in the machine in my laboratory up here, okay? And here you do have a friction coefficient around, well, a bit higher than 0.6. I said before, crustal rocks, they do have a friction coefficient of 0.6. These had friction coefficient of almost 0.8, was a carbonate. So we have a friction coefficient due to the fact that we were slipping the two rocks one against the other at very slow velocity, roughly 50 micrometers per second. And then suddenly we decided to increase the velocity. We have a direct effect, and then we have a huge long-term effect, right? So this is clearly a rock that is velocity strengthening, right? Weakening. So now that is the case, with a classic rotary machine. But then the same can be obtained, pretty much the same can be obtained with a machine that has a spring like this one. And this tells us much more than what this tells us, because this velocity is imposed. The distance is imposed. In this case, instead, we reach pretty much the same velocities, but at the same time, we can see the velocity of slip varying during the slip. And now the question is that an artifact, or is the velocity controlled by those processes that are happening in the fault which will change the fate of an earthquake. Is the earthquake going to grow and become an M9, or is the earthquake going to stop and be only an M5? MW mean magnitude, okay? And we can see even more with these machines. We can see seismic precursors. That is the fault moving, the friction coefficient not going down much, and for somehow aborting. This is an aborted kind of, earthquake, right? But suddenly after, you do have one, okay? Which is very similar to nature, right? We do have all these very pre-seismic events, that comes before big earthquakes, very sequences. For example, in the Apennines in Italy, we do have all those sequences, right? Now, the machine is made in a very simple way. It's a very small machine in comparison to many other rotary machines. And I'm going to show you here how it works. So we do have an engine here that spins loads the spring, and the center of the spring is connected to the bottom sample, and the fault is in between the bottom sample here and the top sample here, and the size of the sample is this one. These are two samples that after an experiment got stuck together, okay? So how does this work? It works in this way. We are loading the spring, so the friction coefficient is going up, and then suddenly the fault decides, I need to release the energy. I can't stand it anymore, right? So you go boom, right? So a single earthquake is just comprised in a very short time, for example, here, okay? In a very short time here, okay? So what do we measure when we do this experiment? We do measure several mechanical quantities. We do have a load cell and a torque cell because we need to define that normal stress and shear stress, which defines the friction. We are going to measure the vertical displacement, and we are going to measure the slip distance, how much the bottom sample rotates into respect to the top sample, which I remind you is fixed, okay? And the other thing we measure are typically acoustic emissions through sensors which are placed close to the fault. And we do have a high-speed camera because we want to look at what happens on the fault while we measure those mechanical properties. And we want to correlate what happens on the surface with the mechanical properties we measure, and eventually with the acoustic emission. Acoustic emission are vibration picked up by kind of microphones, right? I mean, thinking that way. They're not really microphones, but So sound and noise and vibration generated by the earthquake, which is exactly what we do as seismologists, right? We have seismographs and we measure earthquakes, which are nothing more than our acoustic emission in the lab, okay? So this is an experiment that we ran a few days ago. I want to, stress again this thing. I want to make sure everybody is on the same page on how this thing works. And you hear me, and if I'm speaking, saying, and we do have a thermal camera to measure the increase of temperature.
Oh, it's beautiful now.
And we have all
Going very well.
happening, and each single earthquake, you can't see it there. It's really a few milliseconds, 100 milliseconds typically, okay? In that time series that you see here, this zigzag time series over here, okay?
Perfect.
Okay, so the experiment I'm going to show you here has been performed with using polymethyl methacrylate, or PMMA, or plexiglass, okay, or plexiglass, yeah. And why do we use plexiglass? Well, it's transparent, so it allows us to see the fault, right? And it has an homologous temperature similar to granitic rocks, for example, at depths around between 15 and 20 kilometers, okay? The homologous temperature is the ratio between the ambient temperature. If a granite is at 17 kilometers depth, it might be at 750 Kelvin roughly. It's temperature of melting, which is the denominator there. So it's the temperature ambient divided the melting temperature. That gives you 0.7 roughly. And that number is similar to the homologous temperature of PMMA at room temperature 293 Kelvin. In its melting temperature is 418, so also 0.7. Okay. I already showed you the sample, so I don't think I need you to show you to tell you how big it is. We typically apply a normal stress, which is roughly 4 megapascal. That's a limitation of the machine due to the size. Okay. But I have good news. We are going to try this exact methodology on a much bigger machine, which will allow us to simulate much greater depth, right? And the interesting thing that we can do with this machine is to change the loading rate, how quickly we load the spring in order to have a lot of events happening in a minute or much more events happening in a minute, right? So we can control how quickly we load our fault. So typical experiment, right? Start from displacement in blue here from 0, friction from 0, of course. And then we start loading the spring, ramp it up, we get to a maximum of friction, and then suddenly we have an event. And then eventually what is going to happen for pretty much all the experiments in PMMA, the production of melt along the fault is going to make the fault stronger. Is going to create pseudo-tachylite, right? Which some of us might not believe they exist in nature, right? But they believe they do. And they are eventually created in nature as well. We don't know how much they matter for earthquakes. However, what happens here is that this maximum friction here goes up because we are making the fault stronger and stronger. Because we are melting part of the PMMA inside the fault, and therefore every time a new event comes, there is the need of more stress in order to break the fault. And the melt or the pseudo-tachylites are highlighted by this black part here inside the fault. So what you are looking here is the bottom sample, which rotates, against the top sample, and this black part here is the pseudo-tachylite or the melt during the slip. This is a much longer experiment with many, many more events, right? And this point here is where we change the loading rate of our spring. We went from 0.15 megapascal per second to 1.6 megapascal per second. As a consequence, this part here is much more dense. There are many more events per second or per minute than here. What is the difference? Is the difference that we are going to increase the temperature, which is this one, much quicker, and eventually we get to a tipping point where we create so much melt that the fault becomes so strong that the events eventually take off and the events becomes huge. Okay? So this is a typical event, yes. There is a few milliseconds before the event, and this is what we can see with our old high-speed camera, because we have a new one, which I will show eventually at the end of the talk. What you're going to see here is this part, which is pseudo-tachylite, will suddenly break, and it's a precursor. The fault partially broke, did not give up, so it's a failed earthquake, if you want. And now you see that boundary is moving inwards up to when an event happens, up to when a slip happens and the earthquake is gone. And now you see the formation of a new layer of pseudo-tachylite and melt. Okay? So how do we know it's melt? Right? Somebody would ask. Well, this sample here came out from an experiment like that one. They are touched together. The simplest explanation is that we melt the two materials one against the other. We do have SEM evidences. We took samples and we look at the SEM and we really see this carpet of pseudo-tachylite on the rim of the sample, which has been extruded from the fault. And we also see structure like this one, for example, right? Which are clearly partial melt or melt events. Now, because we do have a spring and we do have a torque, a system to measure torque, we can do a balance of the energies involved in the process, right? And this goes back to a theory which has been put forward by Reches initially, that says that the energy flux, which is the energy that the spring is providing eventually into the fault, right, controls the slip style. that's what controls the slip style, is how much energy I'm going to transfer from my rocks, from my mountain range, into the fault. And clearly, it's important how fast I can move it. And how fast can I move stress? You know, the maximum speed is the VP, right? I mean, that's the maximum velocity at which I can move stress around, right? The slip continues until the frictional energy dissipation rate along the fault, or power density, PD, exceeds EF eventually, right? And so we calculate this EF, the EF in the spring, very simple, you know. We have a rotation of the spring, we have an elastic constant for the spring, that gives you the work. The power is nothing more than the time derivative of the work, and then we typically divide it by the area. And then we do have the energy measured by the torque cell, right? The torque cell is telling me how much energy my friction is taking, because the torque cell is what is measuring friction, right? And that is nothing more than the shear stress measured by the torque cell multiply the velocity of slip. And here is an experiment, a single event where the friction is here. Well, this is the shear stress. Divide this by 4 roughly, so you get a friction of roughly 1. And then suddenly here you do have an event where the friction decreases quite abruptly. I mean, the division here is 10 milliseconds, so this happens everything in 20 milliseconds, I would say. And then the friction stays low for a while, even though the velocity has a very interesting behavior. Now, we have been taught that what matters is the velocity. The velocity is the input of our rating state, for example, right? But the friction looks independent from the velocity there, which is interesting, right? And here we do have the energies, right? Of course, there's a gap between the two energies, the friction and the total energy provided by the spring. Of course, we are not considering inertia, the increase of temperature, the production of particles, the latent heat we are creating melt, the radiated elastic energy, which is the seismic wave, and the internal dissipation, which is attenuation. And then here we do have the acoustic emission, meaning the seismograms, right, that we collect when an earthquake happens, okay? And we want to correlate this. And the very interesting thing here is that, well, we do have a precursor. We generate a lot of low frequency noise, like crackling. And then we have a boom. Let me use this, which is when the fault breaks. A lot of seismic energy release that, and that's not interesting. This is all well known. What has been known, what we notice in this work is that there is a big gap of silence just after that big boom. And we believe that that is correlated to the presence of melt along the fault. The melt lubricating the fault is going to lubricate it, and therefore decrease the amount of elastic energy or seismic waves which are emitted by the fault. And then, even more interestingly, after that blank space, we do have an emission of acoustic emission. We have acoustic emissions, right, that are related to the fact that the two energies here are getting together, right? And remember wrenches, right? When they get together, you know, you eventually stop the slip, which is not what happens here. What happens here is that the slip stabilizes. It goes to a constant velocity, and what we think there happens is that we are breaking. The melt is becoming too thick, is eventually fragmenting, which is a term borrowed by volcanologists, and eventually is going to put resistance into the fault, making the fault going slower. And this is associated with the emission of acoustic emission again, with acoustic emission. Is it the case? No. Pretty much all the experiments are exactly like that. These are 9 different events out of the many that we generate every experiment, and they all show the same pattern. Big boom, blank space, and then another burst of acoustic emission. can we look further in this data? Yes, we can. Again, we are after trying to help the community to create a unified theory. Therefore, we need to test the theories which are already there, if they are valid or not. Flash heating and weakening, it's valid, but interestingly, it's valid for a certain extent, for sure for the first part of this slip, and then exactly where we see this acoustic emission, we think there is breaking, flash heating and weakening start deviating from our data, which is interesting. At least we find it's interesting, right? Another theory we can test is the theory of Nielsen, 2008, which tells us when a layer of melt forms within the fault, right? And the number that comes out is 10 milliseconds, and 10 milliseconds for this experiment. And 10 milliseconds is exactly the moment where the velocity goes flat. And the velocity changes. So the process is controlling the velocity, not the velocity is controlling the process. I never said this. And in nature, what is the nexus with nature? Well, first of all, we postulate that if we look carefully in seismograms, especially in big earthquakes that, for example, rupture 400 kilometers of fault, right? And we have enough instruments, we might be able to see during a core seismic slip this part of the fault as melt because it's silent. That part of the fault is rupturing, right? Why this is important? Well, because understanding those processes allow us to create a theory to understand why earthquakes are earthquakes, right? And why do some rupture grow to earthquakes and others do not? Which is exactly the question that we are trying to resolve in the third chapter, right? And the main actors are Caroline Bland and Omar Alamoudi. And this has been done in collaboration with Dr. Harm Van den Donk and Nathan Banks. Big pleasure. And you can find, some information, more information on this paper, which is submitted. You find it a preprint in Autoria. And we are after why in the Ikurangi margin in New Zealand, the north part deforms through slow slip events, not only through those, there are earthquakes there as well, while the south part of the Ikurangi margin does not show slow slip events. We are a few kilometers apart, which for Texas is a couple of counties, right? And still, we have a huge difference in mechanical behavior. The north part creeps, deforms in a slow slip way, right? And the south part generate eventually big earthquakes. And there is a big concern there because eventually they are expecting a mega thrust earthquake, which we hope doesn't happen. This doesn't rule out the fact that in the north a mega thrust earthquake does not have to happen. It could happen there as well, okay? So there are several theories why this might happen. And one of the theories is that, for example, the north is more rough. The subducted plate in the north part is rougher than the south, and this changes, the structure and so on, and allows this to happen. But there is a common belief. Pretty much everybody, Professor Safer Damian is a god on this. He knows a lot of the Ikurangi margin and the Nakai margin, and has been studied this a lot, right? And I believe he agrees on the fact that there is a common belief that, the pore pressure controls the slip behavior, probably. And the pore pressure could be controlled by many things, or at least the pore pressure is one of the big factors controlling the slip behavior. And the hypothesis we try to test here is that there is a change in lithologies, and especially in the quantities of clays between the south and the north. There are less clays in the south than in the north, and the presence of clay is going to control the permeability. The permeability is going to control the pressure that generates at depth, and the presence of overpressure will eventually trigger those low slip events, which do not happen in the south. And clays are finicky materials. They have very low permeability, and eventually I think we collected some evidences that for sure clays might have a role in controlling the timing of these slow slip events, which happen every few years. They last between weeks and months, okay? And this timing is not clear why this happens, right? A bit of about the Ikurangi margin. So the Ikurangi margin is on the east side of the North Island of New Zealand. The Pacific plate dive under the Australian plate there, and you do have a subduction that initiated roughly between the Eocene and the Oligocene here. So when you look at this line here, between this green and this, what color is this one? Whatever. Another green, maroon, brown. That is the delimitation between the backstop, right? The rocks that were there before the subduction initiated, and where all the sediments have been piled up from the Eocene till now, okay? And therefore, if this is the backstop, right? If we collect samples very close to the backstop, we should be able to find rocks which are older than the rocks deposited eventually here. And I want to show you that those rocks are believed to be at the base of the accretionary wedge. The base of the accretionary wedge is the part that does not allow those fluids to get out from the subducted plate. And if those sediments do not allow the fluid to get out, eventually you are going to build up pore pressures, and the pore pressure eventually will conduce to a slow slip event, or to an earthquake as well. So we believe that the rocks that we collected in this area here are in fact representative for the deep part of the of the sedimentary wedge. And this is, kind of supported by other studies. So we collected 4 samples from very young sediments from the Pliocene, the FB12 on the top, which is a porosity of roughly 18%. Then a sample from the Miocene, GB13, a bit lower porosity. And then we went down to the MT07, which is a sample with 7% porosity, very close to the backstop. And we believe that that is a representative rock for the lower part of the sedimentary wedge. And then we also sampled MO02, 6% porosity. That is part of the backstop itself. We measure velocities. Why do we measure velocities, VP and VSs, in the laboratory? This is Dr. Olsen now, at the time was a student. There is Caroline putting the rocks inside the pressure vessel in our lab. And we measure velocities as a function of the confining, well, it's not really confining pressure, but it's a proxy for confining pressure. Yeah, that's confining pressure, roughly. Okay? So there is nothing new, nothing really exciting here, right? The velocity increases as you stress and you compact your rock, okay? The important thing here, that together with the permeability measured on those rocks, where the younger rocks, they have a pretty high permeability in the order of microdarcy, while the old rocks close to the backstop have an incredibly low permeability in the order of 10 nanodarcy, typical of sediments in accretionary wedges. Together, all this data together, they kind of create this picture here. And the fact that we have velocities allow us to correlate the velocities from seismic sections that have been collected, for example, during the Shire project, with the velocity we measure in the laboratory. These are the velocities for, and the permeabilities together for the very young samples. See, permeability fairly high. These are the permeabilities and the velocities for the samples which are much deeper down in the sedimentary wedge, and they have much lower permeability. We kind of propose that this kind of law for these rocks will be, probably better than what is being currently used. this can be discussed. But the very exciting part of this study comes now, when we start looking at the permeability of the fracture rock. Because if a slow slip event is going to happen, then it's going to fracture your rock. And we want to see how that fracture will survive after it has been at depth in the sedimentary wedge, in contact with fluids eventually, right? So we took a rock sample, MT07, the deepest part of the sedimentary wedge. We crack it using a Brazilian test. We generate a fairly vertical fracture. That's a CT image. And we start measuring permeability and compare the permeability to the previous permeability measured. And this is scan number 1. This is this scan here. This is the fracture. And the fracture is an aperture, an average aperture of 190 micrometers, okay? Now we start increasing the pressure and we immediately saw the permeability dropping, and the very interesting thing is the hysteresis. The permeability stays low. Doesn't go back, okay? Like expected eventually. Like for example here the permeability goes down, but then it comes back pretty much on the same path. Here no, the permeability goes down and stays low. Till here, the rock is dry. We are measuring permeability using helium, okay? Now, at day 9, we stopped the experiment because it was Christmas. Or 2 days before Christmas. And then we take again the experiment from where we left it at day 48. It was 40 days in between. This tells you how much graduate students stay in vacation during Christmas, right? So day 48, we took again the same experiment, repressurized it, and the permeability were even lower. The sample, by staying there alone inside the pressure vessel with almost no permeability, the permeability went down. And the fracture became 72 micrometers, in aperture. Okay, now in a sedimentary wedge, there's a lot of fluids. So we are kind of cheating here, right? Okay, let's try to inject a bit of fluid in there. How do we do that? Well, we evaporated water in there. We didn't immediately inject water, right? And by doing that, we obtain a 10 times lower permeability. That's it, okay? And the fracture kind of propped, which is interesting, right? The fracture becomes bigger, but the permeability goes down. What happens? Well, a thin section revealed that you do have expansion of those clays. This rock had roughly, I skipped very quickly on that, but this rock has roughly 15% of clays, 10% of which are illite smectite. I had a picture of Hector. I took it away because my presentation was too long, and I'm going to finish. Hector helped us a lot on this. I don't know where he's sitting. Where are you sitting? Where are you, Hector? Here he is. But there was something bothering me, right? We took this sample, we put it in the pressure vessel, we take it out, we manipulate, we put it inside a humidifier. The measurement of the fracture, how much is due to the fact that we are manipulating the sample, right? So here is where Omar comes in, because Omar built this amazing instrument in my laboratory, which allows to do those experiments without never taking out the sample and take CT images, which, the guys in the CT lab, they are super efficient, they help us a lot, right? So we took another sample, we crack it, and we put inside this machine, we brought to the CT scanner lab, and we started looking at how the fracture was closing as we were increasing the confining pressure. And, we clearly see the fracture becoming smaller and smaller and smaller as we increase the pressure. But the question is, how is the hysteresis? What happens if we come back in pressure, or, more importantly, if we inject a small amount of water, right? So this is the mean fracture aperture as we increase the confining pressure, which is the stress around the sample, right? And this is the permeability as we increase the confining pressure, and the fracture becomes smaller and smaller. But the very interesting thing is that when we injected those, again, 15 milliliter of water, again, by injecting humid air, not injecting directly water, we, I think, achieved the swelling of those clays, right? The fracture, I don't know how well you can see that. The fracture has changed in many places, and not only closed, somewhere it has propped, because the clay, they swell. and eventually they are going to fill your fracture, right? And we achieved, even though the fracture didn't change much, but in some places yes, we achieved a twofold decrease in permeability. Here we are slightly lower pressure than previously. Now, we kind of see that this fracture, they heal in the time of weeks to months, right? And those earthquakes or slow slip events happen every couple of years, right? So what we think might happen in the north of the Kurangi margin is that you do have slow slip which fractures these rocks, which are extremely tight. This increases the permeability, allows the fluid to get out, not generating big earthquakes, right? And then in the time of few months, those fractures reclose, reseal again the contact between the subducted plate and the sedimentary wedge, and then the pore pressure starts increasing again, and then after 2 years, again the fracturing. So, the healing of the permeability kind of controls the timing of the slow slip events. And last year, I presented this thing at the AGU, and Sharan, Dr. Shisharan, right, presented a very similar work on the mechanical properties. And they found exactly the opposite. They found that the mechanical properties of those rocks, they don't heal. So I went on the stage and I was panicking because, hey, I have all these people, right? They will tell me, why do you find exactly the opposite, right? But then in this year I thought about it and I say, this is not one against the other, right? I mean, these two things go together. If you now have a fault which keeps breaking in the same place, right, and it heals hydraulically, but doesn't heal mechanically, that's perfect, right? You keep having slow slip events on the same place, because what matters is how strong is the fault. And if the fault doesn't recover the strength, that's great, right? At the same time, you do recover the permeability, creating conditions that are conducive to slow slip events. That's it. I already said everything here. I just want to say we collect a lot of rocks. We are trying to continue this work. I have to revise the proposal. I will do it as soon as it comes back. And this is New Zealand. Go if you can. And now I do have a lot of students came in fresh, and I'm very happy about that. I'm also overwhelmed, but that's good. So Omar is supposed to, did you send the message? Good. Keep sending it. Yeah. Omar should write the thesis. And I do have working with me and Professor Espinosa Clay, who's a postdoc. He will work on CO2 and rocks. I do have Isabel, which works on attenuation. Jacob works on the Kurangi margin together with Dr. Arm Van den Donk and Nathan Banks. Then there is this stupid person in the center. Then there is Saleh, who also worked on CO2 and rocks interaction. And then I have Enrique and Sarah, which they expressed their intention to work in my group. I'm looking for a student for friction study. I was turned down. Yeah, that happens. Yeah. And again, we want to keep working on the Kurangi margin because it's interesting, and New Zealand is for sure important to check out. Thank you very much. I will take questions if you want.